in progress. And here we go. So this tutorial material is in the Hub's curriculum folder under Rokem-ML. And I'll start with some, let me actually delete or close these other things that are open here so that I don't get too confused, and make this a little bit larger so that I can see it on my screen even. And minimize this. Is this visible for folks in the room? Folks on Zoom, this works? Yes. Maybe. Yeah, here. All right. Okay, yeah, I see some thumbs up here, so I'm gonna move on ahead. Okay, so first, just kind of like an introduction, setting the stage here, what will happen here over the next about 90 minutes or so. This could be a whirlwind of tour of machine learning from, again, you'll see a little bit of code here, definitely, and a lot of the stuff will be explained using code, but the emphasis here is on conceptual framework. You will learn enough machine learning to be really dangerous, I think. Just enough to like start stumbling around. Machine learning is a huge field. This would be like, I was just talking earlier with someone, that this would be like doing a 90-minute intro to, I don't know, intro to biochemistry, right? It's a huge field with lots of intricacies to it. It's highly mathematical in its foundations, and I will show just about no math at all in this tutorial, and try to explain things from a conceptual point of view with lots of hand waving and lots of code, which I think does help. For me personally, understanding mathematical principles is made easier if I can see code that implements those principles. And there are 6 notebooks here, and we may or may not get through all of them, but I'll try to get through the main things that are sort of principles that I think are important. And then you can read through the other notebooks as well. They're quite complete in terms of their details. This notebook that is the preliminaries emphasizes that there are particular variables that you can change that will change the results of certain computations. And this is a good way to explore what happens when you change certain parameters in here. So definitely do that while we're talking and after the fact as you're trying to explore this. Will all be in Python. We'll use machine learning, a very popular machine learning library called Scikit-Learn. I'll increase the zoom again. Just show of hands here. I'm curious who has written code that used kind of Scikit. Who's written code that had to import Scikit-Learn something here? Okay. Okay, so some of you, and that's good. I think maybe this may still be useful for those of you who have used Scikit-Learn, and those of you who haven't. This will introduce you to this. And the installation stuff. Well, let me talk first about the data set that I'm going to use. Some of you who've been here in this room and other tutorials have seen this data set before. It's a data set that's on the Hub and is taken from the Abide 2 study. Here is, so I'm reading it from a CSV file or TSV file here and printing it out. It's a data set that contains information. Each row is a subject in this big study that was focused on autism and had multiple sites collect data from multiple individuals. And there's a variable called group that when it's set to 1 means that that person had a diagnosis of autism, and when it's set to 2 means that person did not have a diagnosis of autism. Was a control, and there's other things here. Subject is unique identifier, site is the site from which this was collected. There's the age of the individuals. Age residual is something we'll come to soon, is pretty much the difference between that person's age and the mean in that site, and that's important. And then there's sex. And then after that, there are many columns, about 1,400 and some columns here on the right that are all derived features from their T1 weighted images through FreeSurfer, things like the area of left V1 and the area of left MST and so on. And so there are 4 different features and 360 regions of interest based on the HTTP multimodal parcellation. And we'll see how we use that. So that's going to be the data that we look at. And in machine learning speak, that data, I'm actually going to talk just about the things from this column to the right here, those are what we call are sometimes is referred to as the design matrix in kind of statistics, and is sort of the observations that we've made about these individuals. And each column here we talk about as a feature of the data, and each row is a sample. So there's N samples and P features, and this is a big matrix in math speak, a two-dimensional array that contains all the things from here on to the right are all numbers that refer to certain quantities like that have units and so on. So these are all floating point numbers. So it's a big array with the same data type everywhere. It's all floating point numbers. And that's the kind of thing that Scikit-Learn expects to see in its normal operation. But there are also demographic and phenotypic data here that are these kind of things on the left that we, for example, might want to use machine learning in order to predict. For example, we'd like to use these features to predict who belongs to which group. That might be an interesting exercise to do. Yeah, and this is just to say this data comes from this paper from Bettelheim et al. Okay, I'll move on now. So that's the data, and we'll come back to this data. Let me step back here and introduce you to some core concepts of machine learning, and we'll come back to this data and how we use those features and samples and those phenotypic data, what we call phenotypic data in models. Before we start, here are some things that we will need. Some of you have seen these ones in tutorials that were held in this room yesterday and today for visualization and for data munging, and we'll use them a little bit, although they won't be the focus of this tutorial. And we can separately, if there's sort of questions about what those are doing, we can take those separately. So we're going to import all of those and also NumPy, which is the main numerical computing package in Python, on which all of this is based. So that, with that all imported into our notebook, let's talk a little bit about what is machine learning. So machine learning, as defined here, is the field of science and engineering that seeks to build systems capable of learning from experience. And that's a very, very, like I said before, that's a very broad field that includes many different subfields. And in practice, what ends up being labeled machine learning is very, very heterogeneous, sort of like the things that get labeled biochemistry. It's a very big field. But there's sort of common features to all of this. The emphasis is usually on developing systems that can learn mostly automatically or semi-automatically from observation of the data, rather than other systems, so-called expert systems, into which we've built in rules. The idea is we observe some data from the world and we build a system based on these observations of the data, rather than from our a priori knowledge of something about the data, where we write certain rules down and then we give it some data and we ask it to apply those rules. We ask it to learn the rules. And then the other thing is that a lot of machine learning is focused on evaluation of those systems that is based on meeting some kind of objective quantitative targets. So this is quite different from what we often do in kind of like normal statistics, where our focus is on comparative evaluation of different groups to each other, comparison between them, and seeing whether there are differences between them. Instead, the emphasis here is not so much on understanding or explaining how a system operates, but rather being able to make accurate predictions from the data. And I'll boil that down a little bit. And there's lots of examples of this kind of discussion between prediction and explanation. It's a really interesting topic in itself to think about. What do we want to do in science? Do we want to make accurate predictions of future events or parts of the data that we haven't seen, or to generalize the subsets of data that we set aside for that purpose, or whether we want to come up with an explanation that exactly tells us what is different between, say, two groups. And the focus in machine learning is more on the former, in being able to generalize, being able to predict, being able to accurately match the machine learning, the system's predictions to, or kind of like inferences to quantitative targets. There are broadly two groups of algorithms, two sets of, or two different approaches to data. The first and kinds of tasks that we might do when we do machine learning, and this will become a lot more specific soon. One is called supervised, and the other is called unsupervised learning. Supervised learning is a fairly typical situation where we have features like those brain features that I showed you before from the BI data set, and we have some phenotype that serves as the supervisory signal, the supervising signal on our learning. For example, in the BI data set, if we had all those brain features and we were to use those in order to create a system that can accurately infer the age of a participant, we would use the fact that we know all those ages of the people in that data set in order to train the algorithm in a supervised manner. That is, the algorithm sees a person's brain features and tries to guess the age of that individual. We know what the true age is, and we can look at the difference between what the system says the age is and what really is the age. And we can use that difference in some way in order to adjust the system so that next time that it sees that data, it's more closer to that target. That's a very kind of, it's not exactly the mechanics of it, but conceptually, that's the idea of the supervised learning. We have a vector of labels, Y, we call these Y, usually one-dimensional vector with n samples as well, right? So age is an n by one column matrix. And then we have, remember, n by p features, and p can be a large number, but then we have the age is this Y is usually just one variable, and we call that sometimes the outcome or the dependent variable. And then X, by convention, we refer to the variables, those features, as X. So that's capital X and lowercase y, and you'll see a lot of these X and Y in the code, and that comes a little bit from the way that this is the notation people use in math in order to describe these kinds of things. Here are some examples of supervised learning problems. Predicting people's age from structural brain differences. We'll do that a little bit later. Determining whether or not incoming email is spam. Predicting a person's rating of a particular movie based on the ratings of some other movies. Diagnosing schizophrenia based on a genetic marker, and we can add to that. There's lots of examples of supervised learning. Supervised learning breaks down further into two different kinds of supervised learning, and you might have already sort of noticed these here. One that is classification problems, the other are regression problems. In classification, we have discrete labels that we're trying to classify. This determining whether or not incoming email is spam is a kind of a classification problem. There's spam and there's not spam, and we're trying to say which is which, and those are discrete labels. In contrast, regression problems are problems in which the Y is a continuous variable, and we're trying to hit the value to be close to the continuous variable rather than a classification. Let's start actually with that one. It's somewhat simpler to start with, visualize and think about as a first problem. So here is an example of data that we might do regression on. So we have Y as a function of X. We've sort of randomly generated here. X is a bunch of random numbers, and then Y depends in some sense on X. But we've added this code here adds some noise to that dependence, and then we plot this as a scatter plot. We don't use necessarily the best API possible down here. Those of you who saw my Matplotlib presentation earlier today know that this is not how I would necessarily always do this, but it works. And then what we're going to try to do here is what's called ordinary. So we have Y, and in this case, X is a single feature. So the P in that n by P matrix, the P is 1. We have one variable Y, one feature X, and we're trying to estimate, we're trying to build some kind of system here that would, given an X, given as close as possible estimate of Y. And one first approach here is called ordinary least squares regression. Ordinary least squares is an analytic solution to that problem. Looking at these data, we can come up with a straight line that goes through this data such that the residuals, the sum of the square of errors between that line and the true y's is as small as possible. So sum of the squared errors as small as possible. Here, in fact, is the solution to that written out in NumPy. The first thing that we do is we take the matrix and we add a columns of ones, and that's to account for the fact that at 0, the line may or may not pass directly through 0. That's called an intercept term. So we add an intercept term to the design matrix, and then we use least squares, which is implemented inside of NumPy. We give it the X matrix, we give it the Y, we add some additional things, and then we get the parameters out over here on this side, and then we can plot the best fit line. So here is the solution to the ordinary least squares, the ordinary least squares solution to the regression problem in this case. And the parameters, there are two parameters here. The intercept, as I said, that we allow for the intercept to vary between, so that it's not, the line doesn't necessarily have to pass through 0. And then we have the slope, 0.62. This can be written down. So our prediction, y hat, the prediction of y is equal to this equation, negative 0.37, which is roughly this thing, plus 0.62x. So if we got a new value of x, we could use this equation, we'd run it through this equation and predict a new value of y for some data, new data. So that's a very simple regression problem. Yes?
Yeah, in previous session, I noticed you always started your PLC with self function. And you, my understanding was that's what you do always, even if you don't actually have self plots, smaller plots in one figure.
Yeah.
Which is not what's happening in this example.
Here, this you mean? Yeah, I could have done what I told you earlier today to do, which is big X equals PLT dot subplots and then replace these with X dot set X label, X dot set Y label, and so on and so forth. And that would have been probably a better thing to do. A lot of this tutorial will not necessarily follow that. It's kind of sloppy, but it's not the focus of the tutorial, so the plotting code is all a little shorter.
But this would be the practice you would suggest.
This would definitely be the practice that I would suggest. And maybe I should rewrite this tutorial to follow my own device.
Can you explain of the last course?
This, oh, sorry, yes. Here we've taken and we've here we fit the parameters. And here, in order to generate this line, we invert the equation in order to, or we run the model forward on a bunch of X values. We generate here 100 linspace per default, I believe, creates 50 values from X min to X max, spanning sort of the range of X values. So there are 50 points here along this line from X, and they're equally spaced. And then here we're doing W0 is the intercept plus W1 is the slope times XX. And we plot that against the values of XX, and that generates then this line. So running the model forward, we're actually predicting a series of Y values to generate this best fit line.
What is the next line? Is anything that
I'm not sure. Sorry, I don't actually know why we did this here. This is not doing anything for us. Sorry, as far as I can tell. Yeah, sorry about that. Unnecessary. Sorry. Okay, what other questions do you have about the regression setting? So again, the important kind of part to focus on here is that we've by observing the data, right, in this line, we're observing the data and learning some parameters. We can then run those parameters through an equation in order to make predictions for some range of values or for new values and so on. And this is continuous in the regression case. These values that we get out here are some continuous values between, in this case, between -2 and 2. Okay, the other setting or the other kind of task here in the classification, sorry, the supervised learning class of tasks is classification. So here there are discrete classes. Here, this has 2 dimensions. Now the setting that we have, X, has 2 columns actually. These are now features of X. And there is a Y, but that Y is the color of these points here. So those points are colored by Y. There are 2 classes of Y. I believe there's 0 and 1. So 0's down here in blue, 1's up here in Y, and each one of these points has 2 values of X. It has X in the first column, X in the second column that determine the position of these points on the XY on this chart. So the first X is here and the second X is here. So that's how that's laid out here. And so, you know, if we have this thing and we might want to create a machine that, or a system or an equation or some kind of thing that given a new point in this plane, we'll say, oh, should this belong to this class or this class? I don't know, if it dropped a point here, should it be blue or yellow? That's the classification task. So, you know, this is a pretty good case, right? Here, you know, for example, we might think about doing something similar to what we did, which is to put a straight line through this space, finding a straight line, the best straight line, such that yellow things fall on one side and blue things fall on the other. This is data that's called linearly separable, because there is actually a straight line that puts all the yellow points on one side and all the blue points on the other side. There's a lot of those straight lines, in fact. And maybe there's one that's kind of the best in some sense. But really in the real world, most of the time things look more like this, right? Where things are not, the data are not linearly separable. There are even worse cases than this one, because there is a straight line you could put here that would at least improve, like kind of like give you maximal classification. In other cases, can't even do that. And you know, it's entirely possible there's no feasible way to perfectly discriminate between the 2 classes, but you can optimize some quantitative criterion here to do as well as possible. Oh, random state, right? So the reason, so I kind of went quickly here. There is in Scikit-Learn, there's a function that makes blobs, right? So here it's making some blobs over here, and random state is a way to fix the randomization. Usually when you run make blobs, let me just not use this and show you what happens if I run this several times without it. Each time it does something different. But if I do set the random state, then I know that it's always going to do the same thing. And it's very handy for tutorials, for example, to know exactly, so that you can, for example, here we also set a random state up here somewhere. I also fixed the random seed here, and that's so that I can write in here that this is the equation, because I know I ran this before and I know that's kind of. I'm not sure I heard, but I think what you said is that this random state is, it goes in and it sets the random seed. Yes, you could do that as well. Yes, you could. I could do, like, I think if I did npdar random dot seed here and set that to 2, that might do exactly the same thing as that. Yes, it does. So yeah, equivalent. But it's easy. It's nice that it's in the same call. This can be useful in many situations where you want to be sure that you're doing the same thing always, like in testing your code and things like that. Yes.
The B input into plot scatter, is that just saying basically color Y? Okay.
Yeah. Yes. Okay. Some classification problems have more of this kind of nature. This is also a classification problem because the labels are discrete, but they're, in this case, it's not 2 classes that are being classified, instead it's 5 different classes that are being classified. So this is also a classification problem, but it's not a binary classification. 2 classes, it's a multi-class classification problem, but also a classification. Okay, so those are the two kinds of supervised learning. Before I move on to unsupervised learning, what questions do you have about these two kinds of supervised learning? And we'll dive a lot deeper into these in following methods. Okay. The next thing is this entirely different family of learning called unsupervised learning. In unsupervised learning, imagine that we did not have labels associated with those brain features at all. We just knew that those brain features, each row there came from a different individual, but we don't know anything about those individuals. We don't know their ages, we don't know their diagnosis, and so on. We might still be able to learn something about the data from looking at the systematic variation that exists in the data, right? If one brain area grows larger, maybe another brain area also grows larger between individuals, right? So there's some common correlations between different brain areas. In fact, everything that Katerina showed earlier today, or most of what Katerina showed today are various forms of unsupervised learning, because they rely on really looking at time series in a brain and not necessarily taking into account some kind of phenotypical variance. So that's an example of unsupervised learning. And then you can do a variety of different things there. One typical thing to do in unsupervised learning is clustering, where, for example, you get something like this, right? So again, we have here an X matrix that has two columns. The first column on the horizontal dimension, the second column on the vertical dimension here. And we get this data, and it's not labeled for us. But what we want to do maybe in this case is we want to cluster these or determine groups within this. We want to assign discrete labels to the data. And sort of this is kind of the best case scenario. We'll look at this and it's very clear that there are groups in this data that we could assign different labels to. And we can do that in an automatic fashion. Right, so something like this.
The type of correlation matrices we were seeing in the talk we were discussing, and we saw some clusters, is that also categories under unsupervised learning? Yeah,
I think the clustering of brain regions into these boxes in Katerina's setting is exactly a clustering problem, and you saw they use very fancy in the InfoMap approach is a really clever way of using information theory in order to essentially solve this problem. So each one of these things that I described so far there are many algorithms that do every one of these things. Right, but again, the world is more complicated, and often, maybe that's ground truth, and this is what we see in our data. And for this case, it's very hard. It would be very hard to cluster this data in a reliable way. We'd have to come up with some idea about how many clusters. One of the problems we start with often is how many clusters are there in here in the first place, right? How many dimensions does this break apart into, and where should I put the boundaries? How do I determine that? And you can come up again with quantitative criteria that tell you what's a good idea to do. Yeah.
I imagine it might depend on what and an analytic approach you're using, but in unsupervised learning, would it be more common to see the opposite, potentially, overfitting, so that you're identifying three different clusters, but in reality
there are only so the question is, wouldn't the kind of typical failure mode here is to look at this and say, there are lots of points here, let's just make a lot of clusters here out of this thing, and where in truth there were three. And that is one failure mode, but depending on the data, you can imagine other kinds of things that might go wrong. If really the ground truth is three, you want some algorithm that will, on average, give you three here, not more and not less, right? If your clustering algorithm is if the points don't fall on top of each other, they're different clusters, that's not a very useful clustering algorithm, because it'll just give you the number, in most cases, it will give you the number of data points that you have. Not a very useful summary of the data. So, right, clustering is often often done on data where there are no true clusters, right? I mean, a lot of the field of this functional brain connectivity has a hard time because it's like, it's not clear. How should you define a brain network, right? There's many ways you could define that. So it makes that very hard conceptually. And you have to go, then you have to go back to the brain and say like, what would make sense here and other kinds of data. So it's tricky. Right, it's not even obvious how many clusters there. It's a hard. It really are. Clustering is a really, really hard problem. If you find yourself in a situation where what you are trying to solve is a clustering problem, step back for a moment and think whether there is another problem you could be solving, or another setting for the problem. Because I think really clustering problems are just really, really hard. Here's one that you could solve instead, which is also an unsupervised learning problem that uses similar data in the sense that you don't have a Y, you just have an X, and is instead a dimensionality reduction problem. For example, consider this data set here. This data set has two features, X1 and X2, those two columns that are again plotted here on these two dimensions. And we don't have any Y, but we look at this data and we might look at it and say, there's a lot of information. If I know the first feature of that person, I might know the second feature of that person with a high degree of certainty, just given this structure. So there's structure in the data that has lower dimensionality than 2. Really, the data itself doesn't really have a natural dimensionality of 2. Really, if we took and we rotated this like that, most of it really falls on one axis. And that's the idea of dimensionality reduction, is to look at the systematic variation in the data and kind of try to compress it down to less dimensions than it really originally has. And that can be a good first step, say, for a clustering problem, is to do this. This is the first good step for pretty much any analysis, to look at the dimensionality of the data through the lens of dimensionality reduction and think about that first. So this is dimensionality reduction. There are many ways to do that. Again, this idea that this data is kind of the structure in the data, and we take that structure and somehow simplify the original data is very common. Okay, what questions do you have about unsupervised learning? Okay, good. I'll continue here then. Okay, so here's the Abide data set again. You'll remember that we have these columns that are summaries of free surfer derived area, volume, critical thickness, and local gyrification. They're signified by these. The prefix here is FS area, or FS volume, or FSCT, or FS LGI for these 4 different features derived from the analysis of this data. And the brain properties themselves, like how they were computed exactly, is not particularly important for our purposes here. But here is again this data. Okay, let's talk about Scikit-Learn. We'll come back to this data in a minute. Scikit-Learn is an excellent Python library. One of the things that it really excels at is, well, 2 things that it really excels at. I'll start with the first one that's a little bit more technical. The first thing that it excels at is in providing very uniform programming interfaces, or APIs, application programming interfaces, to users, people that write software that uses Scikit-Learn, to a variety of different algorithms. You'll see soon that you keep using the same code. You can keep using the same code in order to use to apply different methods of regression, methods of supervised learning, unsupervised learning to data. You get this kind of language that is very uniform. So that's the first thing that it really excels at. It's also technically the implementation is really great. The second thing that it really excels at, that I think is important, is the documentation that is, stellar, simply stellar. You can go to the website here, the Scikit-Learn website, and reading this is like reading a very nice textbook on machine learning. It takes you through how to use Scikit-Learn in a variety of settings with large collection of examples with all kinds of data. It's really, really great. So definitely you want to rely on that. And it's a huge community. It's gotten contributions from and is used by organizations all over the world, both in academic research and industry. And really, it's become a real standard for machine learning. The data in Scikit-Learn is organized pretty much like we've seen so far, right? There's one two-dimensional array always in all machine learning problems, pretty much. One two-dimensional array of n samples with p features that is labeled x. And that's, fortunately for us, this is exactly how the data here is organized. With one small little thing, I'm going to filter my data here. This is a pandas data frame, and I'm going to use the filter function to pull out those columns that start with the FS. And so what I've done here is I've pulled out just the brain features part of this, and this I call that X all here. And that'll be our X for the purposes of the machine learning tasks. And then I'm going to pull out one column out of this, the age column, and I'm going to turn that into a NumPy array by referring directly to the values that are in there. And that's going to be our Y, and that's a one-dimensional vector. I'm hitting Control M8 to add another cell here, just so you see what that looks like. It's a one-dimensional vector, and then X all is this table here. Okay. So let's sort of demonstrate how we use Scikit-Learn via doing a task of brain age prediction. Brain age prediction, we try to create some system that takes that X with all the brain data and tries to predict the age of an individual by looking at some data that has ages in it. Right. In Scikit-Learn, the way that this will work is that we will use one of a very large group of objects in the Scikit-Learn library that are estimator objects. Estimator classes also, those objects and classes in Python, those words mean similar things. These classes or objects will all have a function, a method associated with them called fit that takes some data and learns. And then they all have a function called predict that takes only the X and predicts some Ys, some new Ys for it based on the learning process, right? So the sequence usually of operations here is you have some data, in this case, X and Y, X brain features, Y ages, and you give that to a fit method of some estimator. And then after you've done that, you can take X, either the X you originally used or some other X, give it to the to the predict method and get out some new Ys. These are these Y hats, these predicted Ys. So here's an example of that. Let's see, the thing we do here is to make this a little simpler is we take those 1440 columns that X has, just again to X.shape or X-alls, sorry, dot shape. The shape of this is 1004 by 1440. So we have 1440 features, and we're randomly selecting 5 of those. So we're choosing at random 5 columns to be our X, and we have Y. We did this before, but just to be clear, this is what we're doing here. And then this, so our data for our model fitting will be X and Y. The first model that we will use is linear regression. You saw that before implemented in NumPy. Here we're going to use the linear regression that's implemented in Scikit-Learn. So this is the way that this is imported. Scikit-Learn, written out as Sklearn, has a submodule linear model that has an object called linear regression. And here what we're doing is that we are initializing this estimator object. And at this point, we haven't given it any data. We're just initializing the idea of a linear regression here. And linear regression doesn't take any additional parameters in here. You can you can see what it, let me do this and then I'll show you. You can, by typing Shift and Tab, you can see what kinds of things this can take. You can take, for example, fit intercept, whether or not to fit this intercept term. And that's set to true as per default. So we're just going to leave it at the default, but you could have changed that to something else. And so now we have an object called model, and that model object has a fit method. And to fit it, we give it X and Y. And this is when the model goes from being an unfit model that doesn't have any parameters set, to being a fit model, a middle model that has an intercept parameter and coefficients. In this case, there's an intercept 53.81. That's in years, so that's the intercept of the prediction rate. And then it has 1, 2, 3, 4, 5 coefficients because we had 5 features. So you can think of this as an equation that looks, let me see, like this one, right? Y hat, a predicted age for a new person, is equal to 53.81, which is the intercept, minus 3.94 x1, their value, the value in the first column of x for them, plus 0.02 x2, minus 8.92 x3, minus 0.01 x5. And we don't necessarily know what they are. We chose those at random from the original 1440. But when this linear regression model saw this data, it kind of twiddled around and figured out that this would be the best possible solution. And this is ordinary least squares regression, just like the ordinary least squares regression that we did before, but instead of having one value of x, it has 5 values of x. So you can, it's done in 5 dimensions. Right, and we can notice there's some features here that are much more important than other features for the determination of the age of any individual.
Quick question.
Yeah.
So what makes the OLS regression here machine learning? So like something you could do by calculating out the sum squared.
Yeah, no, yeah, nothing really. That boundary between the boundary between machine learning and not machine learning in this case is not a very hard and fast one. In fact, for this kind of thing, you could go and you could estimate those parameters and their p-values associated with them and so on, and kind of like do this kind of like standard statistics. The thing that makes this more machine learning is really how we're going to treat this. How we're going to handle this thing, what we're going to kind of focus on once we've done this. And that is to generate predictions out of it, right? Which is a little different from the standard statistics. So here we're generating predictions, right? We take our X and we create a Y hat, a Y predicted. And then we can do something that's not commonly done in kind of like standard statistics, which is to take a predicted Y and compare it to the real Y and put that in one of these Seaborn pair plots, or sorry, these are called joint plots, not pair plots. So here we have the predicted age on the x-axis, and here we have the true age on the y-axis. And here, in fact, we have a regression line, linear regression line fit to the prediction quality. It tells us what the correlation is between the true and the predicted values. And this is the thing we're going to focus on, is really like how well does this prediction conform to the best case scenario. This would be a straight line. Every single individual's age would be predicted with 0 error, but that's not the case here, of course. But you might look at this and say, this is good, this is bad, whatever you may judge this in multiple different things. At the very least, you can see that it's capturing some signal. There's some signal about age in this data. Maybe that's interesting. Maybe it's not. And then there's the relationship's not linear. So maybe that's interesting. I don't know, but right. But yeah, we're focused here on learning machine learning and Scikit-Learn, not producing publishable results. So we won't sweat too much what this means, except just to say like, okay, we got from data to now a prediction of this quantity. And here is how Scikit-Learn did this, right? This is the entire code to do that. So that's also kind of neat. The code is very simple. And this is again, just to kind of really hit that home, we could have done the following, which is to import some statistical modeling software. In this case, it's stats models. It's a library that does parametrics, that's kind of like standard parametric statistics, and this is OLS regression as well. And here you get p-values associated with every one of these with this data, and you get all kinds of the standard F statistics and stuff like that to tell you whether or not, you know, every one of these. And then now we know what the parameters are, but just looking at that, which ones are statistically significant, which one are not. But we're not so much focused on this. They're not unrelated. They're related to each other, of course, these two activities, but we're not so focused on this thing. We're more focused on this, on plots like this than the one that has prediction versus true, kind of like how well that worked. And then this is, so that'll be the next thing that we will do is we'll quantify how well did that work. Okay, but let me pause here for a second and see what questions do you have so about this in particular, kind of like this central paradigm of fitting models in Scikit-Learn. Yes.
What they want to do is non-linear model.
Sorry, I couldn't hear that.
To use non-linear models.
Yes, yeah, yeah, you could, there's lots of nonlinear models you could do here. Yeah, absolutely, yeah. So you could replace this with some other model. That's part of the beauty of this, is that you can use something else in here, and then the rest of the code would actually look exactly the same. Yes, so there's a host of different models in there. Some of them are nonlinear. Okay, so let's quantify performance. Scikit-Learn has a bunch of different metrics that you could apply here. Here's one, the coefficient of determination, or the R2 score. So again, we're going to predict Y from our model, and then we're going to compare the true Y to the predicted Y, and that'll give us some number, 0.2. One interpretation of this, which is actually precisely true for the ordinary least squares regression, just approximately true for other things, is that this is the variance explained in the data. And in this case, it's 20%. So this model explains 20% of the variance in the age is explained by the predictions from this model. And you can say whether you can judge whether or not this is a good thing. It's a matter of perspective, a little bit like good for what exactly, but it's not zero. And that in itself might be interesting. And then there are other metrics that you could put here instead, like maybe because this is in years, maybe the mean squared error. Oops, sorry, let me actually do this. Mean squared error is and again, the API for all these things is also uniform. So yeah, this is the mean squared error, 71 years. So maybe that's interesting too. Maybe you can compare it to some other algorithm and then say this is less than this other algorithm. An interesting thing to do, if that's interesting to you. So when you can experiment with that more, I'll just point out that the model themselves, as part of the API, if we have an estimator here, linear regression, that we fit with X and Y, you can also score it directly. So it has a score method that gives you some metric about how well that worked with some new X and Y or the same X and Y. And in the case of linear regression, it is the R2 score, the coefficient of determination. So that they also have, so you go from kind of like, this is a full set of, this is all your model of fitting and evaluation in 3 lines of code. So that's pretty nice. Okay, what questions do you have about this quantification idea? So this is going to be the thing that we're focusing on next. Like, how well does it do? 0.2, that's how well it does. And higher is better and lower is worse. And okay, let's look at a classification example. So again, in this data, we have people who are diagnosed with autism and people who are not diagnosed with autism, and we can do something very similar to what we did before. So here we've selected 3 of the variables, and we're plotting all our individuals on three-dimensional plot. This is an interactive plot also. It's not really the focus of this tutorial, but you can kind of put these three-dimensional plots into Jupyter notebooks that allow you then to rotate and look around at these things. And so everyone here is colored based on whether or not they have a diagnosis of autism, and they're each placed into this three-dimensional space based on the values in these three particular features. Okay, so so could we classify who has autism, who doesn't have autism based on our data? The API that we will use will be very similar to what we used before, but we will be looking at a different part of Scikit-Learn now. So here we're looking at a Gaussian-Made Bayes classifier. Not too important what that means, except to say that it's initialized here, and then we get the data for the group, and we fit it down here. And that's really all that we need to do in order to then score that. And this score for this classifier is the percent accuracy. So we can classify with about 63% accuracy, where we had all of the features here. By the way, we put in all 1,440 features. So plugging in all 1,440 features of derived from the brains of these individuals, we have a 63% accuracy in classifying them as having or not having autism. And again, is this good or bad? Depends on what you're trying to do here. Yes.
I don't see that predict.
Sorry, could you?
Predict. I'm not seeing that.
Oh, yeah, there's not a dot predict here, but I think it does have a GMB dot. Here it is, predict. Right. So if I gave it xall and I did that like y pred here, then now y pred has 2s and 1s, right? Because the original classes were 2s and 1s for have or do not have a diagnosis of autism. So it does have a predict.
We didn't have it first because we were just classifying and getting one with accuracy.
Right here, what we did, we jumped straight without doing the prediction and looking at the prediction and so on. We went straight to scoring this. Went straight to just how well did it do, without looking at the predictions necessarily. There's a little bit more detailed. There's something called the classification report, which is also from this metrics module, where you get a little bit more. I won't go in depth in this for the sake of time, because I've already been going pretty slow, but you get a little bit more detail. The classification is kind of a complicated thing, right? You can think about these different categories. A picture taken from Wikipedia here about like, there's all these different classes, and you might think like, what do I want to do? Like 63% doesn't necessarily capture everything you can about classification accuracy. So I'll let you look at that later on if you want. But for now, the important thing is, okay, we did the same kind of thing, but now instead of, the code looks very, very similar, but now instead of doing a regression task, we did a classification task. The output of that in terms of prediction is now binary, in this case, binary or discrete categories. And it implemented some other algorithm. And I'm not going into detail about what this does, although there's a link here and you can go and look and see what Gaussian-Made Bayes does and try to reason about whether this is a good thing or a bad thing, or how 63% or any of the numbers that appear here, let's try to reason about these numbers and whether it makes sense, whether it's helpful, whether you've gained any insight about autism and its relationship to brain structure. Okay, so I'll pause here. What questions do you have about these kind of APIs and this just kind of like general thrust of the logic here? Okay, so now another example to show you that even if your task is a clustering task, an unsupervised task, there's a very similar API. So we're going to do some processing of the data here before this scaling. We're going to standardize the columns before we do that, and then we're going to select some features. Again, we're sampling in random. So here we're actually selecting, we're using some code here up front in order to select only those rows of the original matrix that have classification of group as 1, as in people with the diagnosis of autism. So here, when we look at X all aught group, that means we're looking only at people who do have autism, and because our question, maybe our scientific question here is, are there neural subtypes of autism? Are there, among the people that have autism, are there different clusters of these brain structures? And then we sample 2 columns, again, in random from this, and we save the column names here, and then we scale it so that every column here is has I think the scaling goes mean 0, variance 1. So they're similar scale, because maybe one is area and the other is thickness or something. They have different units. And here is then a clustering algorithm. So k-means is a clustering algorithm that if you give it a number k, it will find k different clusters in your data. It'll break your data up into 4 in this case, the way that we're using down here, but k, whatever k number, based on a fairly simple algorithm that sort of randomly chooses some points in the space and then kind of associates things and iterates on that until it finds those clusters. The details are not important, too important, except to say, here we're initializing this thing. And notice this time we're initializing it with an input, because this thing does need us to tell us it's something. Remember, when we did the linear regression, we didn't really need to tell it anything in order to initialize the object. And then we're actually fitting and predicting in one shot. So we're going to fit to, in this case, only one variable, right? Because it's an unsupervised learning task. There's only one variable that goes in here. This is this 2-column matrix that we generated here that has some, from the autism group, 2 brain features in it. We give it that X matrix, so it has n rows, the number of people who have a diagnosis of autism, times 2 columns, 2 features. And there's a fit method here. This k-means clustering algorithm does have a fit method that we could apply, but it also has a fit and predict, which is this fit predict method that does both of those things in one shot, because often that's what you want to do. You want to fit and then immediately predict. And so why do that in 2 lines when you can do that in 1 line of code? And low, it gives you 4 clusters. That's by design, because that's what you asked it for. And every individual here gets some assignment. And without going into too much details of the plotting code, here's 2 of the features. Oh, well, we had only 2 features, sorry. Here are the 2 features. And each person here is colored in a color that designates their cluster. You can look at this and ask yourself whether you believe that there are 4 clusters in this data or not. But sometimes you want 4 clusters and it'll give you 4 clusters. There are special points here that have thicker lines around them. And those are what are called the centroids of the clusters. Along the way, while k-means is computing which cluster each individual point belongs to, it also computes a centroid. It's kind of like the average position of that cluster. And here they are. So again, the emphasis is not so much on what exactly k-means did under the hood, but just to emphasize that, again, the API to do that is remarkably simple and similar, very, very similar to what we did before with the supervised learning cases. That's
run repetitions of k-means on one same column because of the randomized starting.
Yeah, so that is actually what's going on here under the hood. It uses k-means plus, which is an algorithm that does this, I think, 100 times with random initializations, then selects the best ones. It's already clever under the hood. Yeah. Okay, so we did a lot of machine learning over the last few things. Let's leave with something a little bit happy here. We will go and we will fit linear regression here, and we will fit this for varying numbers of features. We'll start with only 5 features like we did before, but then we'll go to 10, 20, 50, 100, and in the end we'll fit to everything. And for every one of them, we will fit the model down here, and we will score the model over there. And let's run that. And I'll do it several times for each one. We did do this 10 times for each one, just kind of to get some statistics on that. So that takes a little bit of time. It does 10 times, I don't know, 10 things here, and then produces an array with the results. That's the scores. These are these coefficients of determination. And then after that's done, we'll plot the results here. The plot will have on the x-axis the number of features that were selected, and then on the y-axis, how well we performed doing this. Oh, this is taking more time than I thought it should, but here it comes eventually. Oh, there we go. Okay, and so what we see here is that the more features we use, the better the model does. And in fact, once we get above 1,000 here, the model is essentially perfect. So that's great. Machine learning to the rescue. We've basically predicted with zero error the age of individuals based on their brain structure. So I guess we're done. We've found the perfect algorithm here. Sorry, what problem do you see with this design here? Yes.
Well, you're trading them the same data you're testing.
Yeah, I'm training on the same data. So I'm evaluating here the performance on the same data that I used for training. In fact, you can show that for linear regression, if you have at least, let's say that we have at least the same number of or larger number of columns than rows, and that if those columns are really independent from each other, if the real dimensionality of that data really is larger than the number of subjects, then not only is there one good solution that will fit the data perfectly, there's actually an infinite number of solutions that will fit the data perfectly. So that's the problem here, is the topic of this next notebook here that I'll go to now. So this is also called overfitting. The idea is that when you have this kind of set of data, you want to be able to fit the model to the data, but you don't want to be fitting to idiosyncratic wiggles that are noise. You want the systematic structure of the data to come out. So we'll go next to this overfitting idea here. We're going to import some things here, and we're going to create a function in this first cell that makes some data. This data has an equation that's a quadratic equation. I'll show that here. So here is some data generated from this equation, and has this quadratic structure plus some noise. So this is, again, x is just one number in this case, one column of x, and this is y, the output. We're making 30 points in this case. And then we're going to fit the linear regression model to that. And the linear regression model is not so great for this kind of data. Somehow it captures the data, right? It does as well as linear regression does, but it's got some error associated with it. And it's just not so great. So, we look at that and we say there's more structure in the data that could be captured by a better model. And the problem here is that our model is not sufficiently flexible. It's underfitting. For the sake of time, I'm not going to go too much into detail into what is going in this cell. We're doing something a lot more sophisticated here that lets us then fit a model with polynomials. So now we take, instead of having just the x, we have x, and then we have x squared, and we have x to the third, to the fourth, to the fifth, is it up to degree 10 here. So we have 10 powers of, or actually degree 9 in this case. And so now we have a really complicated model, right? We have all these polynomial features based on this, and it does much better in fitting the data. But now we look at this and we say, this is pretty weird, right? It's like, it does this weird wiggle all the way down here just so it can hit this point up here. Exactly. So the feeling here that this is also a little bit off. And really the thing to notice then is that if you took this model fit to this data, and you took your data generating equation, you generated with some new noise, and you compared those, then things would actually be pretty terrible. That's because in this case, the noise is different, so the points end up in slightly different places. And in this case, the model is overfit to this particular data set. So we want to balance those two things. On the one hand, we don't want a model that underfits the data like this one does, and we don't want a model that overfits the data like this one does. And so we can ask for this one, for example, maybe, polynomial degree 2 would be exactly the right one. And in fact, it would be exactly right for this one because this data was generated from a quadratic equation. Polynomial degree 2 exactly captures that. So, that's kind of the right model here. But and we can play around. There's a widget here that does this. We call the first sample here the training sample. That's the sample on which we fit the data. And then the second sample generated from the same equation, but with new noise, with new random numbers, is this test sample. And we can then, generate different numbers of samples if we want, with some differing degrees of noise associated with that. And then the most important knob here is the degree of the polynomial. And we can see if we up that a lot, the error on the training sample will go down, 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 but at some point the error on the test sample will just go up, 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 up. So here we can sort of start seeing a procedure that would help us deal with overfitting, which is to fit the model on some training sample, play around with some parameters of the model, and make sure that while we are fitting the training data, at the same time, we're not missing completely on the test sample. So in this case, as soon as we go to degree 3, the error on the training sample keeps going down, but immediately the error on the train sample starts going up. And that suggests to us that we should have stayed here where the error was small in both of them. Right? The error, in fact, in this case, because the model complexity keeps growing, you'll always be able to capture more and more of this data. The error will almost always go down as you increase the degrees of the polynomial, but at some point they'll start going up here. And that's exactly the point that you're trying to catch here, trying to increase model complexity just enough so that it captures the data that you're testing on, while also not missing completely this other data. Yes.
So like typically when you test it, right, you get with one shot at that, and you wouldn't want to adjust the parameters in like your classifier again after doing that. So do you have any suggestions for like just avoiding overfitting in general, or is it just kind of like your best judgment of yes or not?
Yeah, so I think the question is, look, you've done this, and now you have your training sample here and your test sample here, and you're going to twiddle this complexity knob here until you get small error on this one while also fitting this other one. But you're going to keep twiddling, and now you're overfitting to this combination of these two data sets. You only kind of get to do that once. And there is a procedure for that, which is I'll show it in the next notebook. Actually, there is a solution for that problem. I think it captures it. I'll go then to the next one here, which is to say there is a general procedure that helps with that. It's called cross-validation. In fact, we already hinted at this cross-validation approach previously. I'll go down here to show sort of the where we're headed here. Is here what I showed you in the previous notebook is this idea that you split your data into train and test initially, and then you train on one set of data, and then you test on another set of data. But I think the further step that actually answers your question is that within the training data itself, you can also split it up such that you do all your figuring out your complexity of the model over here, and then apply that learning to that thing. Now you're evaluating the model more kind of cleanly, and you can keep nesting things like that quite a bit. And you'll need to sit there and think what makes sense for the setting in which I'm working. Let me go back to the top here. Okay, so we're going to get the data. We're going to get all the age and these features, and now we're going to try to apply this idea of splitting up the data and then training on some of the data and testing on some of the data. And Scikit-Learn has a function, train test split, from the model selection submodule that does exactly that. It takes X and Y, and it can take optionally something like the training size, like how are we splitting the data. If it's a fraction, then it will, in this case, split the data exactly in half. So the splitting here, just to make it clear, the splitting here is on the samples. It takes half of the rows, randomly selects half of the rows, not necessarily the top half, but random selection of half of the rows, and assigns that now into a variable called xtrain. Half go into xtest, and then ytrain and ytest. The nice thing about this function is that they're matched, right? The rows of ytrain are the same rows as xtrain, and the rows of xtest are the same as ytest. So they're sort of yoked to each other in the split. Yes.
How do you like know if you don't have enough data to like split it up or do this? If that makes sense. Like, I don't know.
Like the question is, how do you know that you have enough data in order to do this kind of thing in the first place?
Yeah.
One thing you could do is assess kind of the stability of, do the split, and then assess the stability of the model just in your trained data. Like, see, do I have enough data? If you don't, then you might be in trouble, actually. And we often run into trouble of that sort. I'm thinking about a project we're working on right now, where you end up with a small sample of the thing you're interested in, and you have to sort of figure out, am I going to be able to evaluate how well the model is doing given this small sample here? How variable is it going to be? And I think the honest truth is, for us, for example, in this project I'm thinking about, is we're going to have to, in the end, say, here's how good we think this does, and here are our error bars on that estimate based on some procedure that we do to estimate the error bars. And that's how that's the data we have. More data is better in this, and in most cases, yeah.
Thank you.
Okay, so here's the procedure, right? This is the full kind of cross-validation procedure, not full, but a full cross-validation procedure. We create our estimator, the linear regression, we fit it, and then we can score it with xtrain, ytrain. That's the training set R squared. And we can also score it with, we give it the other data, right? It's been fit to this data, and now we're giving it to score the other data. So, remember, here we're giving it all the features, and like before, we got an R squared of 1, which means fully predictive. But then look, in the test sample, it's just terrible. In fact, it's negative, which may surprise some of you who are looking at this and saying, how can an R squared, something squared, be negative? That R squared is a little misleading. The coefficient of determination is not really a squared value, but it has a square. It's called R squared. It's very confusing, but it can be arbitrarily negative, in fact. And when it's negative, whenever it's negative, the thing to think in your head is this model is worse than guessing the mean value. 0 is the R squared of guessing that, say, in this case, age, that the age of every individual is the mean age of the people in the sample. So that's an R squared of 0. That's our baseline model. Anything better than that is better than guessing the average, which is the average is a pretty simplistic model. So anything better than the average is going to be positive there. Anything worse than the average is going to be negative. So this model is worse than the average. And that's because of all the overfitting, right? Remember that those wiggles that went up and down and up and down, it's like doing that in many, many dimensions. It can be worse than just guessing the average, and it is in this case. So what do we do here? Well, we can go back and, for example, randomly sample 200 columns instead and do the same procedure. And we see that when we sample 200 columns, this actually works better. In fact, it's not too bad at all. There's still a gap between the in-sample that's very high here, almost 0.8, and the out-of-sample 0.46. But, the model is capable of predicting age reasonably well in subjects that it's never seen before, just based on their brain structure. It's pretty remarkable. So one thing that's an important kind of detail is here we've kind of arbitrarily divided our data into 2, and then we trained on half and then tested on the other. And one thing that we routinely want to do is to train on all the data, right? We want the model to eventually see all the data. And so the procedure that people will take is called k-fold cross-validation. Here is a schematic of this. You take the training set and you split it up into k parts, and then you fit it on as large or a large part of the data. In this case, I don't know, it's 10-fold, so 90% of the data, and you test on those left out 10%. And you repeat that procedure again and again, leaving out a fold of the data, 10% of the data each time, so that you evaluate on all the data in the end. It might help with your kind of problem as well. And now you get 10 estimates of the error, so you get a distribution, you can report error bars. And one way to think about this is the error is the average across these errors, or the R squared is the average across all these folds. I won't go over this code that in a lot of code shows that this can be really cumbersome to program yourself, except to go back here and just say you can calculate a cross-validation score, again, from Scikit-Learn's model selection module. You tell it, I want 5-fold cross-validation, and then you run, so you create your estimator, in this case, linear regression. You pass the initialized estimator into this cross-validation score function. You give it, in this case, the 200, in this case, we're taking the 200 column smaller feature set, or Y, and we tell it, do 5 times, and then it gives us 5 R squared scores across 5-fold cross-validation. And this is the mean. So this is kind of the average. And that's it. So now we fit, along the way, we fit we did 2 things here. We fit the model to all of the data, but more importantly, every single individual in this data set has had their age predicted from a model that does not include their data in the training set, right? So everyone here has gotten a prediction. We've predicted the full data set without, in kind of like in the absence of that data. It's exhaustive in that sense. So that's nice, and it's sort of comprehensive in some sense. Cross-validation is not so this is really powerful and useful, and is kind of a standard procedure that we do in machine learning. And really at this point, I think I've gotten finally to like this kind of the core of this entire tutorial. I will emphasize here that it's not a panacea. This is a little bit optional, but I'll just point this out. The age distributions across the sites in this data set, just to warn you that we're not ready to celebrate quite yet our scientific discovery, because the sites have different age distributions, and different sites have different scanners, and different scanners have different images. And so it's pretty likely, actually, that's what is going on here is that we're using the images in order to guess which site they came from, and we're guessing the mean for every site or something of that sort based on the data, and not actually gathering important information. Or we're not inferring important information about brain age per se. And we know that because if we instead look at the age residuals, that is the difference between every individual and the mean age in their site, this goes negative again. So, so that's just pulling back to this data and what it is. But, it's not all for naught. And if we do take into account those kinds of confounds and kind of make the right decisions based on these confounds, we could eventually build models that are useful, are predictive, are kind of like tell us about relationships in the data. In this case, we didn't find that, but we could, and we often do. I'm thinking what is next here to do. I will show you this. There's then a set of other procedures that once you do this, so now you've kind of seen the core of machine learning, really, these procedures for estimating model quality by looking at quantitative metrics like R squared and cross-validation in order to ensure that you're not overfitting. Those are really the core ideas in machine learning. Yes.
So in cross-validation, with the parameterization of the model, because in that case, all of them were a linear regression. And so that wouldn't help us with like determining if we should use a polynomial or other So is there any way, I think, so I apologize, I think I'm like stuck in like a classical regression mindset here. So is there a way other than like I-square testing different models with different numbers of parameters to use machine learning to determine which model is the most appropriate for the data?
Yeah. So this, the next thing I was going to say, and I think also helps answer is like, what kind of experimental procedures should we establish in order to determine how we should parameterize our model? Should we be using polynomial features? How should we go about this? And for example, one way to do this is through this idea of a learning curve that I'm creating here. I'll just run the code through here so we get the end to the end of this. Is for example establish a learning curve. Like here in this case, the learning curve is like how well does how good are the training scores and the test scores given different numbers of features, right? And we can look at these curves. So in this case, it's the number of features, right? But it could be the number of polynomial features that are added here. And you would look then at like the training R squared and the test R squared along a set of these kind of things. And I emphasize, I started by this picture because you'll always need to do that over here and then apply what you've learned to a different set so that you don't end up with, doing a lot of experiments here. And I think Russ showed this title of a paper. I tried a bunch of stuff. I think that was the title, something of that sort. Just like basically you'll try a bunch of stuff until you get this test R squared to be really high and nice. And then you'll just stop there and say that's it. You always want to lock away some data that you can evaluate at the end of all your procedures to get a real estimate of the error. And you want that data to be, you want this data to be large enough so that you can estimate that error with some confidence, or at least you want to establish how much confidence do you have in this final error. So this is one procedure, is you use we think of these as hyperparameters, right? Because every time you chose a different number of columns and we fit them all parameters again with this different number of columns. So choose a different number of hyperparameters, and then you split up into test and train, and you fit on the train, and you test on the test, and you get an R squared, and it says something. Here in this case, even given the confound I mentioned before, maybe we don't take this too seriously for these data, but in this case, even increasing. I guess this is sample size. It's not the number of columns. Sorry, it's the size of the training set in this case that we're operating on. But you could do the same thing on the other dimension as well. You can operate on other things as well. We're really close to the end here, so I'll just say that's kind of like the gist of this next pretty long notebook that I won't get to, which is to demonstrate how we do deal with model complexity head on using an approach called regularization, which is to say, we have a lot of columns and we want a model that simultaneously fits the data very well, but at the same time restricts the number of columns that we are allowed to use, and flexibly does that. And in a way that we can dial a knob that says use more columns or less columns. And that's called regularization. It's like selecting a model based on the data, selecting a model that has the right number of features based on the data itself, that has the right level of complexity. And regularization is the approach. It's explained here. There are a few of different approaches. In this notebook, we have something called lasso, which uses one criterion, and then we have ridge regression, which uses a different set of criteria in order to select the number of features which would work well. And this notebook, which I won't, given the time, I won't have time to go over in detail, kind of demonstrates, but I'm actually happy to walk through this at some point, say next week at a breakout session or something, just kind of go in detail into this regularization, because I really enjoy these methods and I enjoy talking about them. And just kind of walk through this notebook in a lot more detail that it deserves, just to kind of show you how that becomes a systematic experimental approach to finding the right level of model complexity given the data, and how that relates to other theoretical ideas as well. So I'll maybe stop here and take questions. I imagine you have many. Yes.
Can you also do validation for supervised learning?
Yes, I think there are methods to do validation on unsupervised learning as well. And that's, for example, imagine the dimensionality reduction setting. You can split the data again into training and test, and then you can take what you learned on the training and apply it to the test and see whether the data kind of spreads in the way, kind of collapses in the way that you would have expected based on what you discovered on the first data set. So like how far away are you, let's say, how far away are you from the way that the data actually collapses in this? Yes.
So if you're collecting data at one time point, you run your model, you get your classification scores and your weights, how would you then apply that to a time point in the future that you may not have collected yet?
Yeah, that's real prediction, right? We talk about prediction here, but and you'll see this also in titles of papers and in descriptions. And often what we're doing is not prediction; it's we're correlating things, right? We're showing an association. What you're talking about is forecasting. Really, the kind of gold standard of this is I haven't collected the data yet. I'm fitting them all over here, and then someday in the future I will collect data. And I want to hit that exactly right? And nothing prevents you from using what I've shown here to do that. And if you're doing it really well, right? The cross-validation picture that I showed here, right? This test set is set aside for as long as you're over here, it's set aside. In fact, it might not even exist yet while you're doing this procedure, right? This test set might actually show up later in time down here and be your gold standard to evaluate on. In fact, in some ways, it's better if it's that way, right? Because you're not likely to kind of peak in some way, right? There are all kinds of ways in which, and this is really a pernicious thing, these models get really complicated, the procedures get really complicated, pipelines that you use get really complicated, and you end up sort of peaking at your validation data or your test data in a way that then affects the model, and now everything, all the assumptions here fall apart. Your evaluation of the model is just wrong. So forecasting is the best case, but it's also really hard. All right, and we can revisit a lot of these ideas next week, both in hack projects and breakouts and so on. But I think given it's 5 o'clock, I'll stop here now, and then feel free definitely to post also to the channel when you're thinking about these things. Like I said, it does no justice to machine learning to teach it in 90 minutes. And I hope that I've made you now dangerous, at least dangerous, by giving you these tools. Enjoy using them, and we'll hack on them. Bye, folks.